Cool. So today we continue discussing conduction in steady state in 1D. And the most important part of what we're going to be seeing today is the concept of thermal resistance. So let's see what that was. So we looked at the case of a plain wall, and although the wall is 2D, because the heat goes in just across the wall and not sideways in the wall, the heat transfer is 1D. And we could write the equations, and those are the equations we saw in week 4 in our unit on differential control volumes. And this is the 1D equation that accounts for transients, that accounts for all kind of gradients, whatever those would be, and accounts also for heat generation. This equation has the only simplification of assuming that the thermal conductivity is constant, right? Because the thermal conductivity was inside the derivative. So if it is constant, we can take it out. And that's the way we got this Laplacian here. So for the particular case of the wall in steady state, this term, the transient term, the derivative of temperature with time, that's 0 and goes away. Also, we're going to consider the case in which there is no heat generation, although if we want, we can. And if you look at the book, they look into the plane wall with heat generation. But let's go one step at a time. So we're going to take this term off too. And we end up with the Laplacian equals 0. But we still can say more, because if it is 1D, the derivative in y and the derivative in z are 0 too. And our differential equation becomes just a second derivative. And there are many ways of integrating the second derivative, but here is a trivial one. And what we saw is something that in reality is very general. What we saw in this particular case is that either the heat rate across the wall is proportional to the temperature difference between the surfaces of the wall. And and that prompted us to say, hey, this proportionality is very similar to the proportionality that is in electricity between voltage and current, in which voltage and temperature are analogs and current and heat rate are analog. So despite heat being so different from electricity, they respond to the same equations in many, many cases when we can represent the heat transfer with using the concept of thermal resistance. So this proportionality in electricity is called Ohm's law. And using Ohm's law, we can define a electrical resistance doing voltage divided by the current. Similarly, we can define thermal resistance by doing delta T, the temperature difference, over the heat rate across that system, right? In this case, we're talking about a wall. And what we saw for the concept of the wall, let's see here, what we saw for the concept of the thermal resistance on a plain wall is that we can calculate the resistance of this wall. And the thermal resistance of the wall is proportional to the thickness. More thickness, more thermal resistance. And we know this because thicker jackets have more thermal resistance for letting us lose heat to a cold weather. So we know this. Thicker is more resistive. Inversely, more area is less resistive. If I have, for example, a bigger wall, I'm going to lose more heat because the wall is just wider, right? Even if the thickness is all the same. So the resistance as a total heat rate is inversely proportional to the area. And also depends on the material of the wall. So if the wall might be made of Aluminum or might be made out of cork. Aluminum is a very good heat conductor. Cork is a very good heat insulator. Not the same thing. How do we account for that? With the thermal conductivity K down here, in which if it says if the thermal conductivity is low, for example, cork or styrofoam or fiberglass, then the resistance is going to be high. In addition, we looked at the concept of resistance per unit area, which is a terrible notation because in reality, resistance per unit area is resistance times unit area. And but it's a concept very useful. And if we apply it to the concept of a plane wall, we see that this resistance per unit area is thickness divided thermal conductivity. And why is this good? Well, this is a useful concept because it doesn't depend on the size of the wall. So if I have a bigger or a smaller wall, I would account for the size with the area, but the properties of the wall in itself are taken care in the resistance per unit area. Okay, resistance per unit area is higher with thicker walls, is lower with more conductive materials. So let's look at the first problem that would be very difficult to solve just by standard heat transfer, but it becomes very easy to solve by using the concept of thermal resistance. So let's consider heat flow, heat flux across two walls. So the heat goes through one wall and then goes through the other wall. This is not a trivial problem at all. But using the concept of thermal resistance, it's going to become so much easier to do. So what is the equivalent circuit here? The equivalent circuit would be these two resistors in series. How would you know if you should use resistance in series or resistances in parallel? This is a criterion. You look at the flow of heat. If the flow of heat goes first through one, for example, let's say heat is flowing from left to right. Heat is going first through this wall number one and then goes through wall number two. This is a series circuit, and we're going to represent it this way. For parallel, of course, we see that the flow of heat goes simultaneously through two parallel paths. It's two different paths. We will see that soon. But for now, let's look at this one that is resistors in series. And so here we have this battery that represents the temperature on one surface of the left wall, and another battery that represents the temperature on the other surface in the opposite surface of the other wall. And the heat is going to flow from one to the other. If it was left to right in this schematic, flows left to right in this other schematic too. And as heat goes first through one wall and then through the other, we see the same. Heat goes first through one wall, and we are going to call this thermal resistance R1, and then goes through the other wall, and we're going to call the thermal resistance of the other wall R2. Important points here, that we know that if we have ground and here we have a battery of TS1, so this point here is at the voltage of TS1, which means this is at the temperature TS1, and TS1 here is the outer surface of one of the walls. So this is the surface temperature of wall 1. Similarly, this one we have here on the right is the surface temperature of wall 2. What is this thing in between? This Tm is the temperature right here at the interface. Let's assume in this case there is no no contact resistance. We can account for that too. I'm not going to do it now, we're going to do it later. let's say there is no contact resistance. So these two walls have the same temperature, right? These two opposing walls touching each other, and it's this temperature here. So this is a very simple electrical circuit. And how would we calculate the heat flux? Well, the heat rate is delta T, Ts1 minus Ts2, divided the total resistance. And or we can do it in heat fluxes. Q double prime is delta T over R double prime. Exactly the same thing. The only difference now is we have a reference area. Okay, and what is total resistance? Because these are resistors in series, the total resistance is the sum of the resistances. And so we have total resistance is R1 plus R2. That would be L over Ka, that is the resistance for wall 1, plus the same thing for wall 2. This sum we have here is what we had seen here before. When we see this equation, for example, this equation for total resistance, there is a lot of black pixels here, right? It can look intimidating, but we know where we are coming from. And we don't need to memorize any of these. It's just we see this sum and we know, oh, okay, these are a series of resistances. The heat is going sequentially through these resistors. And the expression of each of these are, oh, they are the same expression because, of course, it's the expression of resistance of a plane wall. It's not about the math. It's not about having lots of subscripts and lots of Greek letters. It's just knowing two terms, what is each term, and we know where each term comes from. If we did it in resistance per unit area, the equations look simpler, and to some extent, they're also more meaningful because we don't need to worry about the area. This would be universal for walls of any area. This is the way we would calculate heat flux given the temperatures. And we're going to see a concrete example in a second. But the beauty of this is that we can say, okay, and what is the temperature at the interface? Which very often it matters. Because you know TS1, you know TS2, now you know the heat flux. What is the intermediate temperature? But we can calculate it because the heat that is going through the resistors is all the same. I'm going to delve into why it is all the same in a second, but the heat is all the same. So now that I know Q, I would know that, for example, for wall 1, the delta T between TS1 and Tm, right, is Q times R1. So from here, I can solve for Tm. If I wanted, I could have done the same, but with wall 2 and do Tm minus Ts2, and that equals resistance of wall 2 times the heat flow that we know, because we just calculated it. So why is the heat flow the same? Let's say we were to put a control volume anywhere in these walls. Let's say a control volume across like a little flat control volume somewhere. Let's say here. Or let's put the control volume right at the interface. Let's put it right at the interface. So we have the heat coming by conduction from wall 1. And then the heat going by conduction into wall 2. I'm arguing that the heat that goes out of conduction by Q of the wall 1 is the same heat that goes by conduction into wall 2. And the reason for that is that if in this control volume I'm talking about, these two heat flows didn't balance out. I would have a Q in different than a Q out. And let's forget about the volumetric generation right now. And that means we would have a Q stored. And if we store heat, what do we have? We have a transient, right? Because the heat stored was the derivative of enthalpy with time, or the derivative of temperature with time. If I store heat, the enthalpy goes up. But we said that in a transient system, the derivative of temperature or enthalpy with time is 0. So I can have no accumulation in steady state. And what it means is that the heat that goes into a place is exactly the same amount of heat that goes out of it. And that's the case here. That's why we say heat is constant, because wherever we look, as much heat comes in as it goes out in any control volume we might look at. If it was not the case, we would have accumulation. Okay, so let's look at an example in concrete. So this is an interesting example. It is very simple, and we're gonna take it one level up later today. But let's say we have a wall that is made out of brick with stucco on the surface. These are the type of walls in my native Argentina, where I didn't see snow until I was a teenager, right? That's not the wall you would do here in Canada, but it is a good wall for an example here. And we're gonna see why we don't have these walls in Canada. So let's say for this example, that the wall is 6 inches of brick and 1/4 inch of stucco. And I'm going to impose now on the surface of this wall 20 degrees. That would be the inside. And let's say that the outside is minus 10 degrees, is outside. In reality, this should be the temperature of the air. And we're gonna see soon how we deal with that property. But for now, let's say that the wall was at minus 10 outside and the wall was at 20, has a side at 20 on the inside. I have the thermal conductivity of brick and stucco here. And let's say that this wall has a surface area of 15 square meters, right? That would be the cross-sectional area for heat conduction. It's not one side plus the other side. It's just the area through which the heat is conducted, 15 square meters. And I put here what the cost of energy is. That is an example I did a couple of years ago. I'm not too sure these are exact numbers, but we're not all too far. This is what we pay in Alberta, $369 per gigajoule of gas, and what is that? Almost 6 cents per kilowatt hour of electricity. Isn't it funny? They give it to you in different units, but we're gonna put them all on the same basis now for this problem. So, if we want to know how much money this wall is costing us in winter, we have to calculate how much heat goes through the wall. And to calculate how much heat goes through the wall, we need to calculate the heat flow through these 2 stages of conduction. First the brick, then the stucco. And let's do it per unit area first. And then we multiply by the total area to get a final result. So for the brick, we have the thermal resistance per unit area is L over K. And this would be 0.24 watt meter squared per Kelvin per watt. These units don't have a universal value. So these are the right units, but I cannot tell you anything intuitive that 0.24 is big or small. However, when I do the same business for stucco, I get that for this wall, the thermal resistance of stucco is much, much, much smaller. We're gonna see what it means soon. And of course, why is it smaller? Because it's thinner. Does the thermal conductivity change significantly? No. 0.635 and 0.726, more or less the same. Definitely the same order of magnitude. but the thickness is very different. And the end result is that although these two materials, brick and stucco, have similar conductivity, the contribution to thermal resistance is significantly bigger for brick and very, very small for stucco. I add up, because it's a series circuit now, I add up these two resistances and I get a total resistance that is actually not all too far from the resistance of the brick alone. We're going to discuss that in more detail. So now that I have the total thermal resistance, I can calculate the flow of heat. So this would be, in this case, let's talk about fluxes per unit area. And we have delta T over R. 20 degrees on one side, minus 10 degrees on the other side. So it's 30 degrees difference. And the R double prime we have here, and it gives us 120.6 watts per meter square. Actually, this is a fairly high number. And you're going to see how high it is, because if now I multiply by the 15 square meters, to give you an idea, 15 square meters is the size of a living room wall, right? It's maybe a little bit more than that, but it's not even a whole house. It's just one side of a house. It would be the size of a very tiny cabin, right? And if I multiply by the cost, right, by the cost of energy after converting to the proper units, we would get that this wall alone cost us $17 per month in gas. And if we are heating up our house using electricity, which we don't do here in Alberta, and we should never do, would cost us $78 per month. Electrical energy is so much more expensive than thermal energy. I think it's crazy that we use electricity in most of our ovens, right? If we use gas, it would be a lot cheaper. In any case, we just did a calculation that tells us in money how much it costs to keep a house warm. And using these conductivities of stucco and brick, by the way, they're in the list of material properties in the recommended textbook. We are so powerful now. You can go measure your house and do the calculation. Now, because our houses are made with drywall and insulation, not brick, the calculation is a little bit more difficult, but we're going to see more and more details. By the end of this week, you would be able to calculate the heat losses in your house. Okay, so I want to touch briefly on the concept of dominant resistance. Let's go back to our stucco, brick and stucco wall. We saw that the total resistance of the wall is almost all given by the brick. Look, the total resistance of the brick is 0.24, and the total resistance is 0.2487. Tiny what the stucco brings to the table. If I forgot to account for the stucco, the calculation would have been more or less the same. What does it mean? It means that the resistance of the brick, in this case, is dominant. That is the one that gives us the ballpark of the calculation. The other resistance of the stucco is a detail. The more details we have, the more accurate we are. But for the sake of being quick, we forget about the details. If they are not dominant, they're what we call secondary. If they are secondary, we are not committing a major sin. And sometimes it's so convenient to forget about those details that if the price we pay is not too high, that's not a big deal. So look, if we had neglected the stucco, instead of calculating 120.6 watts per meter square, we would have calculated 125. nobody is going to make calculations that are that accurate, right? Or measurements. Making a measurement this accurate is difficult. So in some cases, we might want to neglect what is secondary. But even if we don't neglect it, it's super important to be aware that often we have one resistance that dominates over all others. If we don't, if for example, both resistances are more or less the same, are of comparable value, we say we're in an intermediate regime, right? If the wall is, as we discussed, brick dominates. If the wall was made out of stucco with thin veneer of brick, we would say then we have stucco being dominant. And if the stucco and the brick were more or less the same resistance, then we would say that's an intermediate regime. This was the case for the case of series resistances. The bigger one is the one that dominates. We're going to see, and I want to anticipate this, that if we have parallel resistances, most of the value of the resistance is given by the smaller resistance. And the dominant one would be when the smaller resistance, especially when one is much smaller than the other. We're going to see this in a second. But what is dominant is not always what is bigger. Is what influences the result the most. That's the definition. In series, what influences the result the most is what is biggest. In parallel, what influences the result the most is the smallest one. Okay. We just talked about thermal resistance of a wall. We talked about how we can combine the resistances in a way of getting calculations for a composite wall. We did a calculation for a wall that is made out of brick and stucco, but I said, okay, let's assume that the indoor temperature is exactly the temperature on the surface of the wall, and the outdoor temperature is exactly the surface on the outside of the outer wall. All right, but you might come back to me and say, but how about convection? Don't you have convection heat transfer between the air and the wall? I'm gonna say, yeah, absolutely. And convection has a resistance too. So let's look at it. So if we look at the heat that is exchanged by convection, we have this equation here, in which the heat by convection is surface area times convection coefficient H times delta T, surface temperature minus the temperature of the fluid away. So I can apply, you see, again, we have a proportionality between the heat rate, and the temperature difference. So I can apply, again, Ohm's law for heat transfer and define the resistance, the thermal resistance of convection, that would be delta T over Q, which would be, if I pass this Q, the Q dividing here and the AH dividing, is 1 over HA. More interestingly to me, if we look at the resistance, thermal resistance per unit area, is resistance of convection times area, 1 over H. Outright, 1 over H, right? So now we can make calculations that are similar to our composite wall, in which we had 2 layers of wall. We can say, let's start with this. Say we have 1 layer of wall and convection. Now the heat needs to go through 2 stages. First, it goes through the wall and then goes through convection. We're gonna see that as heat goes through, is transferred by convection, it goes across a boundary layer. Boundary layer is a concept you already heard in fluid mechanics. This is crucial for us to understand convection. Right now, we're playing with convection just using a simple formula, but we're going to see all it means later on in future weeks when we study convection. Okay, so let's say we have a wall that is at temperature Ts1 on one side. I'm imposing this temperature just for the sake of making this problem simpler. And outside, I have T infinity, that is the temperature of my fluid. And let's say I know my temperature of the fluid outside. And let's say I don't know the temperature of this surface of the wall. So how do I calculate the heat flux? Here, okay. There would be a series circuit of resistors in which one resistor accounts for conduction through the wall, and the other resistor goes through something that is invisible because the air is invisible, but goes through this boundary layer in the air, right? Whatever it is, we assign this resistance of convection to it. So goes first resistance of conduction, then resistance of convection. Here outside, we have this other battery that represents the temperature of the fluid outside, T infinity. Most interestingly, this point here is between the resistance of the wall and the resistance of convection. The resistance of convection happens all in the fluid outside. The resistance of the wall happens all inside the wall. And this point in between both, that point is the surface temperature of the wall against the fluid. For example, if you're measuring heat loss in your house, you know the temperature in your house and you would know the temperature outside, but you don't know the temperature on the wall. You can bring a thermal imaging, like the people who are drywall inspectors, and those measure temperatures of the wall, but it's so uncommon you would know the temperature of the wall. The thermostat in your house measures the temperature of the air inside your house, but it doesn't know the temperature of the wall. And actually, if you touch the wall, you're gonna see that typically it's colder than the air inside, right? So this point here in this series circuit is the temperature of the surface of the wall. How do we calculate it? Same way that we calculated the intermediate temperature between two walls. So the level of power of the things we can calculate is increasing significantly. We went from saying, I just know some random heat transfer mechanisms, to saying, I know how to calculate a wall, whatever that is good for, to say, I know how to calculate a series of walls. Now it gets interesting because many things are layered. To say, hey, now I know how to calculate a wall that has convection outside. And that is reality. That is reality. So let's see, let's go back to our brick and stucco wall, and let's calculate it properly. And let's say that in reality, 20 degrees was the temperature of the air inside our wall. And minus 10 degrees was the temperature outside of the air outside the wall. That is reality, because nobody measures temperatures on walls, but everybody measures temperatures of the air. And what I made here with this dashed line is the thickness of this boundary layer, which right now means not a whole lot to you, but I'm introducing the concept little by little because we're gonna go deep into it in a few weeks from now. Similarly, on the stucco outside, we have this dashed line indicating the thickness of the boundary layer outside. The outer wall has this temperature Ts1. So sorry, the inner wall has a surface temperature Ts1, which we don't know. And the outer wall has a surface temperature TS2, which we don't know. We know the temperature of the air inside and outside, but not the temperature of the surface of the wall. And let's also say that inside, very realistically, we have only natural convection, because if everything goes right, you don't have wind inside your house, not in winter. And let's assign here a convection coefficient of 10 watt per meter square Kelvin, as we always do. Ballpark, it's not too bad. And let's say outside, yes, we have wind. And because we have wind, we're gonna claim that it's a forced convection with coefficient of convection of 100 watts per meter square Kelvin. The rest is the same old what we just discussed. How we solve this problem now? This very realistic problem. Well, very realistic if we have an Argentinian house in Canada. A house in Canada that has drywall and insulation and drywall again, and the drywall itself is made of cardboard and plaster, right? Has many, 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 many layers, all of which you can calculate, all of which. Using, for example, the properties that are in the book, or sometimes the properties are tabulated by the companies that make these housing components. We'll discuss more on this later. So for our Argentinian wall in Canada, we would have now 4 resistors. 2 of the resistors we're familiar with. This resistor here was conduction through the brick. This other resistor here was conduction through the stucco. The 2 new resistors are thermal resistance of convection outside and thermal resistance of convection inside. So we have been building little by little, 1 wall, 1 resistors, 2 walls, 2 resistors, 2 walls with convection inside and outside, 4 resistors. The batteries are the same batteries as before, are the batteries that give us the temperature of the air inside and the temperature of the air outside. The calculation is going to be the same as before. What is the heat flux? Well, it's going to be delta T over resistance. What is the difference now? What is resistance? Resistance now is going to be the sum of all 4 resistors here. 2 of the resistors we knew. There are 2 new resistors, that is convection inside and convection outside. If we said inside we had natural convection at 10 watts per meter square Kelvin, 1 over H is 0.1. For outside, we said forced convection, 100 watts per meter square Kelvin, 0.01. All right, I'm going to add them all up, and it's what I have in this line. And what do I see? Look, the brick was dominant, the stucco was very small. Convection outside, that is forced, is very small resistance, right? I'm talking about resistance. Very small resistance means heat can go fast. And resistance of convection inside, that is by natural convection, look, is 0.1. This is significant. 0.1 is comparable to the 0.24. 0.1 is way bigger than the resistance of the stucco and way bigger than the resistance of convection outside. So I can do the calculation and I get that the heat flux through the circuit is 83 watts per meter square. It's a lot less than before. If we multiply by the 15 meters squared, we get that accounting for the convection inside, and outside, we would be, this wall would be costing us $12 a month instead of $17 a month. Convection has been our friend. And going back here, by looking at these values of resistance, we know that the resistance of the stucco was secondary. We knew from before. Now we know also that the resistance of convection outside forced convection is negligible too, is secondary, right? And but the resistance of convection inside is not negligible. It's of more or less of the same order. This is an intermediate regime, right? In which both convection inside and the brick are comparable. In Canada, we don't use brick. We use these super insulating walls such that, yeah, the resistance of that wall will be way bigger than the convection inside. So I'm going to calculate now the temperatures of the surface of the walls, the temperature of the surface of the wall inside and outside. That is the temperature, if you touch the wall, that's the temperature you would feel. And what do we see? We see, let's start with the outside. In the outside, doing the same procedure we did before, we would get that the wall outside is at minus 9 point something degrees. The air was at minus 10. So in the outside, the temperature of the wall, on the surface of the wall, is more or less the same as the temperature of the outer fluid. You know what this means? This means that when the convection is very intense, the surface of the body that is convecting is very close to the temperature of the very close to the temperature of the fluid, right? And we had discussed this when we talked about something that would have a very high Biot number. When the Biot number is very high, is the case in which we have an intense cooling or heating action, intense convection on the surface of a body, and the surface of the body is more or less at the same temperature of the fluid outside. This has practical implications. Let me give you an example. Imagine you're making a sword and you want to quench the sword, right? And you're going to quench the sword with water, right? The water is at 20 degrees C. It gets to a point in which the jet of water is intense enough. The surface of the sword is going to be at 20 degrees C. And you can go crazy having bigger and bigger jets, and things are not going to change. This is totally non-intuitive. Way back in time, when before people started to develop alloyed steels, they wanted to quench big chunks of steel. And they would quench the surface, but the heat took forever to get inside. And they were trying to quench it more intensely. And you know what? It was exactly the same. Because this convection on the surface became secondary. And whatever you do to it, it doesn't matter anymore. For those of you in MARI, the solution, you know what it was? To make alloyed steels that would become hard, would turn into martensite at slower heating rates. But heat transfer had reached its limit. Very interesting. Okay, so we just talked about the outer surface of a wall in which the convection cools it down to pretty much the same temperature of the fluid outside. But inside, the convection is natural convection, is very weak and gentle. So that acts as an insulator. And we had a significant temperature jump. If the temperature of the room inside was 20 degrees, the temperature of the wall, of your brick wall, when you touch it from the inside, when you touch the brick wall from the inside, it would be at 11.6 degrees. Your air surrounding you is at 20. If you touch the wall, it's at 11 point something. It's colder. It's cold, right? Very, very, very interesting. Of course, if you touch your walls now, you're going to see that they're much warmer than 11.6 degrees because we have good insulation. If you have poor insulation, then the wall gets that cold. We have the power to calculate this. Another interesting tidbit. So let's calculate our heat loss by radiation. So by convection, I would do my heat loss of me standing here is my 37 degrees or 33 degrees, whatever the temperature of the surface of my skin, against the 20 degrees of the air in my room. But if I'm in my Argentinian house in Canada, my walls would be at 11 degrees. So the temperature of surroundings is not 20 degrees. The temperature of my surroundings would be 11 degrees, and I would be losing heat by radiation with a temperature difference between my 33 degrees of my skin and 11 degrees on the wall, not 20. This is a case in which it's quite clear the difference between temperature T infinity, the temperature of the fluid surrounding us, and T surroundings, the temperature of the walls surrounding us. All right, so I just mentioned heat loss by radiation, and that can be assigned a resistance too. It's with a trick, because we have seen that radiation is not linear, because it's T to the fourth. It's not delta T outright. However, we can cheat a bit, and as I mentioned many times, the problem is not cheating, the problem is being caught, right? Like if we are gonna make a simplification, as long as it's a simplification that is good and takes us good places, it's okay that it's not exactly true. So in many cases, we can say radiation can be calculated much like convection, but assigning to it an equivalent, a radiation equivalent convection coefficient that has nothing to do with convection, but looks like convection, including the proportionality between Q and delta T. Of course, the proportionality constant happens to be not so constant, but we call it constant, right? And in many cases, that's okay. And in those cases in which it is okay, we would calculate the resistance of radiation per unit area, right? Is 1 over H radiation. Used to be 1 over H for convection, now it's gonna be 1 over H radiation. And this so far is, and when we do it in total heat flux, right, would be 1 over H radiation area. Radiation is interesting because radiation goes in parallel. I'm a given surface, right? Imagine we have a wall that has convection and radiation. So heat, let's say we know the temperature T is 1 of the wall. Heat would go through conduction through the wall, by conduction through the wall, this is this resistor, and then goes out by convection, as we have just seen. But in addition, this same surface, TS2, is losing heat by radiation. At the same time, that's why they are parallel paths. I can stop convection, I can have a vacuum, and I will have no convection. But guess what? I have radiation. That's the case of the thermos. Thermos, the high level, the high class thermos, they pull a vacuum, so they do away with radiation, with convection. So they only have radiation, and then they paint it like chrome finish, so the emissivity coefficient is super small. So these resistors are not yet parallel, because this one is has a battery at T surroundings, and this one has a battery at T infinity. This is not the same. It's not this is not a parallel circuit yet. But in many cases, either because they are exactly the same or because they are similar enough that we call them the same, if both are at the same temperature, let's say both are equals to T infinity, then it is a parallel circuit. And look at this. This starts to become a somewhat more elaborate electrical circuit. From the point of view of electrical circuits, this is a very easy one still. But the heat transfer problem we're tackling is incredibly complex. But we can do it using this methodology. So I think this is a good point to stop. I'm going to pick up on this on Friday and finish this unit on thermal resistance. I'll see you all then. Thank you.